All right, any questions before we get going today? You gotta speak louder. What? Oh, okay, we're not going over the homework today. There will be a review session before the first exam, and we can go through all the homework then. Or if you want to come to office hours and go through specific problems, that's okay too. There also will be final answers for the homework, not the entire solutions, just final answers posted probably in about 2 days, it would, I guess. Maybe I gave you guys a little bit more this time. Any other questions?
You said people have to affect inverse cost.
That's a homework question. So again, office hours or email or wait for the review, which I wouldn't recommend for something like that. Other questions?
And be submitted in the wrong format.
Okay, so yeah, I got a shockingly high number of like people asking to resubmit this time. I don't know what's going on. Here's the deal. You guys should be careful with your submissions, right? If you do it before the deadline, right, and you mess something up, you can send me an email with the full PDF version of everything, the updated one, and say, please grade this one. It's gotta be before the deadline though. Okay. In general though, I want to discourage that because if that happens too much, like, all right, sure, first homework assignment, I got like 10 emails on this stuff. Okay. But if that happens continuously, I'm probably going to take that away and do something else instead. But recommendation is be careful with your submission. But if something goes wrong, then let me know and work on it. But make sure it's before the deadline. Anything else? Okay. So last time we were doing impedances, right, for electrical circuits, and today we're going to finish up our electrical circuits. So impedances, right? Can anybody remind me what the definition of impedance is from last time? Right, and so what is a resistance? It's what over what? Voltage over current, right? That's what an impedance is, right? Except it's in the Laplace domain, right? So we had for a resistor, the impedance of a resistor was what? The resistor's value is R. What is its impedance? R. If we have a capacitance C, what is that impedance? 1 over C times S, right? And if we have inductance L is its value, what is its impedance? LS, right? Okay. So I see folks online getting that too. For today, let's repeat one example, the same circuit that we had earlier, where we have a resistor, we have an inductor, we have a capacitor, we have a voltage source acting on our system. I'm going to call this VN here. Maybe I'll make it lowercase this time. All right, this is C, this is L, this is R. All right, and I'm going to say our output here, we're going to measure the voltage of this capacitor here, right? And I want to get a transfer function from our input to our output. So what is our input in this system? Vn, right? That is going to be U, right? That's our exogenous like force acting on our system, right? That's our voltage that's coming in externally to act on our system. We'll say it's a control input for now, right? Our output is voltage of that capacitor. And I want to use our impedances to get our transfer function here, right? This instead of doing the time domain method that we did last time, right? So what do you guys recommend to do? At the end of last class, I remember everyone raised their hand and said that they remember doing impedances. Maybe just hadn't called that before. But I want to get a transfer function from our input to our output. What ideas do you guys have? Start out here. Let's try and go step by step. Yeah. So label voltages and currents, right? Probably not a bad idea to start out with, right? I would agree with that. So I'm going to say our voltages and currents here. I'm going to say this is the R. This is going to be VL. And then VC, which is the same thing as Y here, right? And then maybe we have a current, well, we definitely have a current that's running through this system, little I, right? Not a bad first step. Okay, what else? What should we do beyond this point? Voltage law, so we want to do impedances, right? So maybe we want to involve that before doing the voltage law. I think the voltage law will probably come into play here, but maybe we want to do something with our impedances first. Right? How about we have these three passive elements? Oh, you got an idea? Not quite sure what you mean by that. Right, so DI/dt, well, LDI/dt, you mean for the inductor, right? That's the time domain, right? And our impedances are the Laplace transform of that, right? So you're on the right track here, but we want to use our impedances for this. So what are our impedances like? They're like resistors. They're generic resistors for any of these elements, right? So why don't we draw this figure again? But like a Laplace transform of this figure, where every element is replaced by this box here. And this box is a generic resistor, a generic impedance. Right? So it's like we're taking a Laplace transform of everything here. And this is going to be ZR. This will be ZL, ZC. Right? This current here we'll call big I of S now. And this is U of S, right? Laplace transform of our input U, right? Right. Impedances are just turning everything in resistors. Why don't we draw our figure out so it kind of looks like that right now, right? Okay, so let's replace what these values are here. We actually just went through them already, right? So that first box, the impedance is just R, right? Second box, the impedance is L times S. Third one, 1 over C times S, right? And I'm going to add in all our other labels here. We're still measuring this guy. So this is still VC of S, or we could just say Y of S if we want to take a shortcut, if we can in this case. We can't always. This would be VL of S. And this would be VR of S. All right. Where do we go from here? Yeah. Hold on. So let's break it up into pieces here. You said characteristic impedance. What do you mean by that? I've never actually heard that terminology before here. So a total impedance is what I would call that, but sure, you could get the total impedance, and for a lot of these problems, probably getting the total impedance for your circuit could work out here, right? So if we want to go about it that way, we certainly can, right? I'm trying to think, is that going to be our fastest way here? Yeah, probably is going to be our fastest way here. So your recommendation is to get a total impedance. How will we get a total impedance? I'm having trouble following you. Your answers are not succinct. I need to figure out a way to understand you here. I think you're saying the right things, but I'm not 100% sure. Let's hear from somebody else to maybe get consensus on this. Exactly, right? We have resistors in series, resistors in parallels. We know those relationships, right? In this case, it's only resistors in series. So if we wanted to just represent this by one equivalent impedance, right? One total impedance, right? We would just sum all of those together. Right? Let's use the tools that you guys have known for a very, very long time. Right? So what is Z total? What is our total impedance in this case? R plus LS plus 1 over CS. We can leave it in this form for now, but if I usually ask for a total impedance for a problem, I don't want to leave it in this form, similar to, I think I said in like the second class or third class, right? I want to get this into some sort of like polynomial over a polynomial, right? In terms of S. So we may want to simplify this down at some step here, but we can do that in a second, right? So what does this actually gain for us? We found our total impedance, but I'm looking for a transfer function Y over U. Is Y equal to Z total? Is that what this figure says here? What is our output? It's a voltage over our capacitor. So first of all, our output is a voltage, so it can't be an impedance, right? Maybe our transfer function will be impedance. It's the voltage of this specific element here. Right? Multiply what by what? So we're applying, I guess you could say, Kirchhoff's voltage law here, right? Or even technically elements in parallel, I think you can make the argument for here, right? Where you're saying, what's the equation you want me to write down here? Right? I of S is the total current going through the circuit, right? U of S is our total voltage, right? And that's our impedance, right? I guess it's more like using like elements in parallel here, right? Okay, how does that help us? So we got the U part there, and we got Z total, but I'm looking for Y over U, right? How does Y get involved in this? All right, so this is like, we could rewrite this as Z total of S is equal to U over I, right? That is like a definition for impedance, right? But we're still looking for Y over U, right?
You need to write I of this. C, I of this.
Getting closer, you're on the right track here, right? But how can we do that? It's for this simplified circuit, it's the total impedance, total current, and total voltage, right? That's our definition of impedance.
You're gonna multiply the current in a certain time to keep passing.
Okay. Can you, if I were to write this down as an equation, what are you trying to say here?
Y of S equals 1 over CS times.
So let's try it, write it a different way in terms of impedances, right? The impedance of our capacitor, ZC of S, right, is equal to 1 over CS, right? Well, what is that also equal to? What's the definition of impedance for any element? It's the voltage of that element over the current of that element, right? What's the voltage of our capacitor? Say it louder. VC, which is also Y of S, right? What's the current going through our capacitor? IS, right? So if we can solve for I of S in terms of that total impedance and U of S, right? If we combine these two equations here, and really this one as well, right? We can solve for Y over U. Right? So if we have, let's go with this one here. Z total of S is equal to U over I, using our definition of impedance like we always would, right? We can also say that this is I of S is equal to, what is it going to be? Z total, but the inverse of that times U of S. Is that correct? Yeah. right? So we get U of S over Z total, that's I of S, right? And then we also know from here, Y is equal to 1 over CS times I of S, which we just solved for. Let's plug that in right here. Right? We can see then, just move that U over. Y over U is 1 over CS times 1 over Z total of S, right? This is not an acceptable answer to me. I want this fully simplified, right? So let's simplify it, right? What is a simplified expression? If we want this in a more polynomial form, how could we express this impedance? Right? How can we, or just how can we simplify this expression to something a little bit easier to manage? Right? We want that polynomial form. Any ideas? Or maybe you guys just want to take a minute and simplify it down for me. But I want something that looks like something S squared plus something times S plus something. Right? That same form that we were talking about in the homework, right? That's what we want this transfer function to end up looking like. One over RCS plus CL maybe plus 1. Let's see. I don't think so. Maybe. I think that R is in the wrong spot. I think what we should end up getting, or at least one form of it. These are zeros. I think we should end up with a 1 over C. All right, so I'm just going to simplify this down to a 1 over C times LS squared plus R times S plus 1 over C. Something like that. Just scroll up a little bit here with the glare. Where's the extra C coming from? Anybody else get the same thing? I could have made a mistake in my notes here. You get the same thing? So we should end up with, well then, so you ended up with a C here, right? Right? So yeah, it's the same thing. I just divided by C. I did it a different way because I did the impedance simplification earlier on, right? Should be the same thing, right? I divided every element by C on the top and the bottom, right? Is that the same thing that you guys got? Yes? All right. Need to make a note in case I did something wrong. But it sounds like we all got the same thing here, right? So I would say in a lot of cases, right, depends on the situation. If you want to get a transfer function for a circuit, it's probably faster to do the impedance method. Now, that is not always going to be true. It really depends on what your input and output is going to be. Depends on how complex that circuit is, right? And it depends on what your own strengths and weaknesses are, right? So in general, I don't know if I'll force you guys to do one method or the other. Maybe on a homework I would. For an exam, I'm not sure about. I'd have to think about it. Probably using impedance method is going to be the faster route. And on exams, you guys are going to have a limited amount of time. So you probably want to take advantage of that, right? But maybe there are some cases where time domain stuff is a little bit better to work with. All right, any questions on impedances? I'll probably upload another example or two online for you guys to work through, or if we get time at the end of the class, which I doubt at the rate that we're going here, we can also go through another one. All right, so now we're going to go over something that was probably touched on in your 3333 class, I don't know in how much detail. I kind of glossed over it a little bit. We're going to talk about a special circuit called the operational amplifier, or op-amp for short. All right. So op-amps are used for a variety of different things. You know, I guess some core examples I would say, I just want to make sure I cover the big ones, right? Scaling input to output voltages, right? Kind of like transformers, but a little bit different. And others are used to implement control, which that kind of deals with the scaling the voltages, right? We will deal with operational amplifiers in terms of like our circuits and stuff like that. I don't know when we get to the control stuff, if we're going to focus on passive versus active circuits and things like that, which is where op-amps come into play. But we will at least talk about them from a modeling perspective here. And I'm not going to go through every detail, the entire proof of how to get the equivalent impedance for an operational amplifier. But I'm going to focus on the big picture so you guys get the core things here. So op-amps, or let's go with our, I think, inverting op-amp. So we have an input voltage, VI, and I'm going to say that we have a resistor here, R1, and we're going to have another resistor that's connected out here, that's R2, but this first one is going to connect to the actual op-amp here, right? The op-amp has like two inputs. This is minus, this is plus, and it has two pieces for our outputs. Right, so it kind of has like a voltage going in and a voltage going out here. Op-amp is typically represented by letter G here. That is the gain that's acting in this system. And we have some sort of output voltage that's acting on here. The resistor connects down here. Then we have the ground piece, which is going to connect to all these here, as well as this one over here. So this is all part of ground here. This is what a inverting op-amp typically looks like. Have you guys seen this circuit before? How many of you guys have? Show of hands. Show of hands, not answering. Okay. All right. So this is our input voltage. This is our output voltage. Right. These are resistances. Right, they are outside of the op-amp itself, but this is technically like a full op-amp circuit, what we're looking at here. And then we need to define a few more things here. Let's define the current going through this resistor, I1. This is going to be I2. This is going to be IA here. And the voltage across these two elements here, that's VA. And then, like I said, this is our gain G. That's how we're going to boost the voltage from the input to the output here, right? This is our typical op-amp circuit, right? Now this looks a little bit confusing. So another way I would rewrite this using the assumptions of an op-amp, actually not even at this stage. I'm going to redraw this into a form that looks a little bit more familiar for a circuit, where we're still going to have that resistor, R1. We're still going to have that branch off to R2. But then instead of this whole triangle thing that we got going on here, so I'm just going to have this piece float out here. VA is just going to float out in space here. It's the voltage difference between this point and the ground. And then instead of doing our whole triangle thing here, let's draw out just like our output voltage. And then right here, instead of the triangle, we're going to have that gain times VA, or negative gain times VA. And this is going to be our output, right? Looks a little bit more similar to a circuit that you would be dealing with, where we have a voltage source that is negative G times VA that's going in here. So the voltage over here, right, is going to impact what the voltage is over here, right? That's going to be coming out of our system. Right? Let's redraw this one more time. All I'm going to do is I'm going to put these two guys, they're in series, right? These two guys kind of look like they're in series if we're saying that this is like multimeter or something that we're measuring. And then this is also going to be on its own in the middle here. So all I'm going to do is shift this down, shift this over here, shift this over here, just redrawing the same thing a little bit differently here. So we have those elements in series, that's VI, and then R1. Right, that is actually going to be in parallel with this right here. So this is VA is going to be existing down here. Again, it's just a voltage difference between that point and ground. And then these are also in parallel with resistor R2. And that negative G times VA, those two guys are in series. And then it's like we're measuring, or this is our output. This is where the power is going to go for this. All right, so we have an input voltage circuit for things that are going on in here, and then an output voltage that can connect to power some sort of device, like let's say a motor, for example. Okay. Right, and if we want to talk about in parallel, negative G times VA is equal to V0, and VA is equal to negative V0 over G. Right. Now, I'm not going to go through the entire proof here, but the big assumptions for an op amp is that an op amp draws negligible current. What that means, right? This is IA here, right? Because this one was IA here. This one was I1. This one was I2. Right? An op amp doesn't draw a lot of current. It doesn't take a lot of power to use. Essentially what we're saying. We're saying IA is equal to 0. Right? Other assumption that we have, an op amp has a high gain. What that means is that G can be approximated as approaching infinity. And these are the big things that we're working with here. All right, so let's start by I'm not going to go, again, not through the full proof, but I want to go through the basics here, right? We can see that there are 3 pieces that are in parallel. This is in parallel with this, which is in parallel with that guy, right? So we have voltages in parallel. VI minus R1 I1 is going to be equal to VA, right? Because they're in parallel with each other, which is equal to negative V out over G, right? That earlier relationship that I had, right? All 3 of these pieces are in parallel. Oh, wait, no, sorry. One more piece, R2 I2 plus V out, right? This is in parallel with this part, which is in parallel with that. All right, it's our first major equation here. Second major equation is to just apply Kirchhoff's current law, right? So what does Kirchhoff's current law state for this? It does have to do with deal with nodes, right? So what node are we going to look at here? Probably like right here, right? Right, that's where currents are coming in and out, right? So what does Kirchhoff's voltage law say, or current law? Right? Current in is equal to current out. That's because that node can't store any energy, right? It's just an empty little like piece of wire or something, right? So I1 is equal to IA plus I2, right? That's what that says right there. But we just said that IA is approximately equal to 0 with our assumption. So what do we end up getting? I1 is equal to I2 approximately. Right? Now we're going to use G approaching infinity, right? And we're going to essentially use these three equations here. We can go through a whole lot of math about how G is approaching infinity, what is the limit for different things here. But what it simplifies down to is that V out is negative R2 over R1 times VI. That's what we end up with our op-amp. So this entire circuit, all that complexity here reduces down to saying that if we have those ratio of our resistors here, the negative of that times the voltage going in is what the voltage is going to be coming out of the circuit, right? That's what an op-amp does. This is specifically called an inverting op-amp. Now, I'm not going to spend the time going through the entire proof, but if anybody wants it, I can post it online. It's also in like almost every standard controls and modeling textbook. So you definitely can find it there. Maybe not in the exact same format as what I'm doing here, but that's what an op-amp does. So these are our key equations here with our op-amp. I1 is I2. This guy right here, this is actually the main one. So if you're going to memorize one, it's going to be that. But this guy here is also important. Okay. Now, what if we had an op-amp with instead of resistors, but just generic impedances, right? What do you think is going to happen? So this is VI, I guess VI of S technically. And instead of having R1, I have Z1. Instead of having R2, I have Z2. And the rest of the circuit looks exactly the same. This guy's got to connect here. So, not asking to go through any math here, just asking you to use what we've learned so far in this class to say, if you were to guess the relationship between V out and V in, what do you think it would be? Yeah, he raised his hand. Say it again. The negative, though, right? It's an inverting op-amp, right? We can go through the proof again if we need to, right? But we don't, right? This is what an inverting op-amp does. It says that the transfer function between that source voltage and our output is this. That is the more generic version of what our op-amp behaves like. Okay, so this is our key equation that we're going to use, but the other ones may be relevant as well. Any questions up to this point before we start? I don't know if we'll be able to finish, but we'll start an example for our op-amps. Is that glare getting in the way of you guys seeing it? I assume it is, yeah. All right. All good? Can I move on here? All right. So let's do an example because this will be in the homework. Take homework number 3. Oh, by the way, homework number 2 assigned today at like 1 or 1:30 or something like that. So keep moving forward with it. If you did not submit homework number, wow, that's loud. If you did not submit homework number 1 in time, you have until the final solutions get posted, which I want to say is going to be Sunday. Remember, you'll get 2 points off, but it's better than submitting nothing at all. So I recommend doing that sooner rather than later if you forgot to submit. All right. Let's now do our inverting op-amp in a circuit. All right, we're at least going to start it out here. Do we have a question online? Not, I'm gonna mute. Okay. All right. So I'm gonna draw the same op amp that we had before. Just a nice little resistor R1 there. Resistor R2 over here. All right. Same triangle. Half the time I'll forget to put these signs in here, but it doesn't matter too much. We're always going to be dealing with inverting op amps in this class is what I'll say. So we have our typical op amp that we were working with before. Still with our ground. But now what I'm going to do is instead of a voltage source, I'm going to connect this to another circuit. That circuit has a current source. I'll even just do IN of S. I'll take our Laplace transform for it. No, let's do IN. In the time domain. And that is connected to another resistor here. I'm going to call it RN. And then a capacitor CN. Right. And using, I think, the 4 equations that we went through earlier, we're going to be able to get a transfer function from our input to our output. This is still going to be our output for now in this example, right? And our input is now going to be that current source, right? So this problem has changed a little bit here. Okay, so we want to get a transfer function from IN to V out. Okay. So ideas for where to start here. What do you guys think? Let's hear from somebody else. You participated a lot today already. Ideas, yeah. So transform everything into impedances. I like that idea, so let's do that. All right, so we have our current source. It's going to be IN of S. Then we're going to have an impedance for RN. What should that be? ZR, but what's ZR going to be? Is it R? RN, right? It's got to be that value in particular, right? That's a mistake I see quite often is people just drop like the subscripts and just assume that they're all like the same value or something like that, right? It's whatever the value is for that resistor in particular. All right, let's draw this part down here. What's the impedance for our capacitor going to be? 1 over CN times S, right? We have another resistor here. That's going to be R1, right? And shoots off. We're going to have R2 up here. I'm going to keep the triangle for now. But now this is going to be our output is VO of S. Right, and the rest is the same. Okay, not a bad first step here. Other ideas? Oh, and this connect. What else can we do? Transforming everything to impedances, if possible, probably a good idea. Make our lives a little bit easier here. Voltage out over, what is it? I'm not sure what terms you're talking about. 1 over CNS, right? So we're getting close there. Let's actually, so what I recommend is an intermediate step here. And then let's label all our currents and voltages here. And then I think what you're saying is going to come to light pretty quickly here. So what I recommend, so label our voltages and currents, right? VR in, right? This is the same thing as before. This is I1, right? That was the current going through that resistor. This is I2, right? Except we're doing the Laplace transforms of it. If you want, you can put IA here, but we know that's approximately equal to 0, right? And then what I recommend, I think where you're getting at here, is let's label this voltage here. Instead of calling it V in of S, right? Just to have the same notation as before, how about VI of S, right? This is the voltage that's going into our op amp, right? It's going to be very similar to what we had in the first case, right? But instead of a voltage source, we have a capacitor which has its own voltage, right? One other thing we may need to label here is the current going through that capacitor, IC of S. I'm not sure if that will be relevant or not, but it could be useful. Okay, so ideas moving forward with this now. So the way I see it is that we kind of have like two halves to the circuit, right? And one half we've done already. Idea? Which voltage? You gotta be specific. VN? Well, we don't want to solve for VN at the end of the day, right? So I think it sounds like you're starting on this side based off of that description. I recommend starting on this side, right? Haven't we done this circuit before? Right? We literally just did. We have a relationship between VI, the voltage that's going into our op amp, and V out, right? What is V out of S over VI of S? Say again? And then what's Z2? Right? We know this relationship here, right? We know that V out of S is equal to negative R2 over R1 times VI of S. And I think that's what you were getting at, right? This part of the circuit is mostly done. We're going to need it for one other piece here, right? So what have we just done? We've taken that entire piece here. I'm going to draw this one more time over here. IN of S. This is RN, right? This is 1 over CN times S. Right? Ground is somewhere over here, right? And then the rest of all this stuff, which we don't really need to worry about, that's our inverting op amp, right? It doesn't really matter what's over there anymore, right? Because now we've connected it to our voltage over this capacitor. We will need it for one more piece, though, here in this particular example. All right. Okay, so now we know the relationship between VO and VI, right? But that's not what I'm looking for at the end of the day. I'm looking for VO over our input, right? So how can we get that? This is probably the trickiest part of the problem. Okay, Kirchhoff's current law, right? Why not? Let's write it out. So what is Kirchhoff's current law going to say? Okay, so what does it say for this problem? IC of S for the capacitor, right? Okay, that may be a useful tool that we have here. Other ideas? Let's see, will we even end up using that? I think we do at some point. Yeah, we will. That's definitely one piece that's going to be important here. Parallel voltage law. Well, what do you want me to write down for this? We have a current source, right, which does have a voltage over it. So if you're going for the parallel part, I think you're going for, that may make things a little bit more complicated, but you could use it. Other ideas? What about those 3 or 4 equations I said that we're probably going to use at some point? All right. What about VI minus R1 times I1, right, is equal to R2, I2 plus V0? So essentially this piece here, right? This piece is also probably going to be relevant, right, for that equation. And this piece also could be relevant for it. So let's write them all out. Our earlier equations that we had, just with the Laplace transform, VI of S is equal to R1 times I1 of S, R2, I2 of S, plus V0. Right? We also had I1 is equal to I2. And then we also know just from earlier, right? VO is negative R2 over R1 times VI. Right? So maybe, just maybe we can solve for I1 in this equation in terms of our other variables that we actually care about, right? So let's combine these guys together, right? VI minus R1 times I1, right? That's equal to R2 times I2. But what's I2 based off of these equations? It's just I1, right? And what's VO? R2 over R1 times VI, right? We can now solve for I1 in terms of VI, right? If you go through this, it simplifies down to 1 over R1 times VI of S. This is a roundabout way of going about it, but this is at least thorough, I guess, let's say, right? But I1 is just going to be 1 over R1 times VI, right? Now we can take this piece here, right? Maybe that'll be useful if we combine them together. So IN is equal to IC, which we don't know yet, plus I1, right? I1 is going to be 1 over R1 times V of I of S, right? And now we can solve for IC here, right? IC is going to end up being IN minus 1 over R1 times VI of S. From there, we can use the impedance of our capacitor, right? VI of S, the voltage of our capacitor, is 1 over CN times S, IC of S, right? We plug those in, we combine them together, right? And suddenly we're going to have a relationship between IN and VI using this method here. And I think we're just about out of time here. So I'm going to write that stuff down. Maybe I'll upload the full solution online. But what we'll end up with is R1 over 1 plus R1 CN times S is equal to IN of S. That's VI, right? And if we know VI in terms of IN, V out of S, which was negative R2 over R1 times VI of S, we combine them together. And suddenly we can get our full transfer function for this system. Right, the R1s are going to cancel out and we're going to end up with negative R2 over 1 plus R1 CN of S. And we end up with our transfer function for our system. Okay, that's all the time we have for today. I'm gonna post this full solution up online, just a little bit clearer in case rushing through things made it a little bit confusing, but it's gonna be more or less the same. I'm also gonna throw up a few more impedance and maybe even time domain examples online. We'll see. All right, other than that, enjoy your weekend. Don't forget about homework number 2.
It's-